Good morning. This is lesson 6.2, the standard normal distribution. This is a normal distribution of raw scores. So if we are looking at this from what we learned in lesson 6.1, mu is that center score, which in this case would be 20. Sigma, which is the standard deviation, is the difference between mu and the score to the right or the left. So if we take 22 minus the mean, we get 2. And each one of those scores on the distribution of raw scores is 2 units apart, which means that the standard deviation is 2. The normal curves we've been working with have been filled with raw data. To standardize the data, raw scores are converted into z-scores. This is the formula with which they are converted. The x is the raw score, mu is the mean, and sigma is the standard deviation. Subtracting the mean from the raw score and then dividing it by the standard deviation gives us the converted score, which we call the z-score. Let's convert the raw data from the normal distribution that we looked at the beginning to a standardized table. We will use the formula z equals x minus mu divided by the standard deviation. So what is mu in the standard normal distribution? We are going to take the mean, or the score that's in the middle, subtract the mean from it, and divide it by the standard deviation. That's going to give us 0. In the standard normal distribution, the center score, or the mean, is always 0. Sigma in the standard normal distribution can be found by using either score on the right or the left, subtracting the mean and dividing it by the standard deviation. We can take 22 minus the mean, which is 20, divided by the standard deviation of 2. We get 2 over 2, which equals 1. In the standard normal distribution, the standard deviation is always 1. So we can add another 1 and we'll get 2, and we'll add another 1 and get 3. On the left side of our distribution, it'll be 0 minus 1, minus another 1, and minus another 1. This is the standard normal distribution for any set of normal raw scores. When you are looking at a table, the number of standard deviations between the x and the mean. So, for example, between the raw score 26 on the left and the mean, which is 20, is the difference between the x and the mean divided by sigma. So 26 minus 20 is 6, divided by the standard deviation, which is 2, is 3. And in the same place where 26 is, in figure 6.2, we have 3, which is 3 standard deviations from the mean. If the original distribution is normal, the corresponding z-values will have a normal distribution as well. When we convert raw data to z-scores, we use the formula z equals x minus mu divided by the standard deviation. When we want to convert z-scores to raw data, we solve for the score. So in this case, we would multiply both sides by sigma and then add the mu. Or x equals the z-score times the standard deviation plus the mean. Given mu equals 20 and sigma equals 2, what is the raw data for z equals negative 2.5? Okay, using the formula on the right, the raw data, or the raw score, is going to be negative 2.5 times the standard deviation, which is 2, plus the mean, which is 20. Negative 2.5 times 2 is negative 5, plus 20 is equal to 15. If z equals 3.5, then the raw score is 3.5 times the standard deviation, which is 2, plus the mu, which is 20, or 7 plus 20, which equals 27. Area and probability, both of which are the area under the curve, are used interchangeably, like radians and degrees on a unit circle. Now we're going to use the table in the back of your book, specifically tables 5 and 5a in Appendix 2. Table 5 looks like this. We want to find the area to the left of z equals negative 2.16, which is going to be right about there. You can tell it's going to be a very small area. So we're going to go down the left side of the table until we find negative 2.1, and then we're going to go across the top of the table to find that hundredths place, which in this case is 0.06. Then the score 0.0154 is the value for negative 2.16. Now that value, 0.0154, is just a little bit more than 1.5%. And that means that the area under the curve is about 1.5% of the total area under the curve. Let's do that again. This time, let's use a positive number. So this would be in table 5a on the right-hand side of your book, in the back at Appendix 2. Let's say that let's say that z is equal to 3.42, which is going to be right about here, which is right on the edge. Okay, so if we want the area to the left of that, that's almost 100%. Okay, so we're going to go down to 3.4, and then 2/100ths of, and I know you can just barely see this, and we end up with 0.9997. Okay. Now let's look at the right-hand side of the table. So if we want to find the area to the right of z equals negative 1.35, okay, so negative 1.35 is going to be right here on the table, and this is the area that we are looking for. Okay, the area under the curve adds up to 100%. So normally you read it from left to right. So at z equals negative 1.35, we are getting that blank area on the left side. We want the right side. So we're going to find out what the left side is, and then we're going to subtract it from 1. So we're going to do the same thing we did before. We're going to go down to negative 1.3 on the left-hand side, and then find 5/100ths up on the right, and then we're going to get 0.0885. Now that's the left-hand side. So we want to subtract that from 1, and we're going to end up with 0.9115, which is just a little bit more than 91%, which makes more sense when you're looking at the actual area under the curve. Let's do that again. This time we're using table 5a, And we're going to find the area to the right of z equals 1.26, which is going to be just about right there. Okay, now left to right is the area on the left of 1.26 is going to be more than 50%. We want the other part of that. We want the complement. So we're going to figure out what that is, and then we're going to subtract it from 1. So we're going to find 1.2 and then 6/100ths across the top, and that gives us 0.8962. Okay, clearly that's more than 50% because that's almost 90% of our graph. So we're going to subtract that from 1 in order to get the right-hand side. And we're going to end up with 0.1038, which is a little more than 10% of our graph and makes a little more sense given the picture that we have below. There are some assumptions we can make about this graph. For example, any area to the left of z equals negative 3.49. Okay, so to the left of this tail on the left-hand side of the graph is going to be about 0. Also, any area to the right of z equals positive 3.49, okay, to the right of right here on the graph, is going to be averaged to about 1. Now let's take a look at finding some ranges or probability intervals. These are spaces that are in the middle of our graph. So for example, let's say we wanted to find the area from z equals 1 to z equals 2.5. Okay, so in the first two graphs, we have z equals 2.5, which from left to right is the greater area. And then we have z equals 1, which from left to right doesn't cover quite as much. So we're going to subtract the greater area minus the smaller area. And that's going to give us this range in the middle in between these two. So 1 is less than z is less than 2.5. Now, in order to figure out what that probability or area actually is, we have to find out what those values are. So looking up 2.5 on table 5A, we're going to get 0.9938. Looking up 1 on table 5A, we're going to get 0.8413. When we subtract those two, we're going to get 0.1525. All right, let's look at that again. So let's say that we want to find the area from negative 0.68 to negative 1.5. Okay, so from left to right, 0.68 is actually the greater area. Okay, and then from negative 1.5, that's actually the smaller area. And then that interval in between them, when we subtract, is going to be negative 1.5 to z to negative 0.68. So negative 0.68 is at 0.2483. Negative 1.5 is 0.0668. And when you subtract them, we get 0.1815, which is just about 18% of our graph there in the middle. All right, and that is pretty much it for lesson 6.2. Make sure that you complete your notes and then take a look at the book assignment. If you have any questions, shoot me an email.